This title's called Treatment Order is the Cheapest and Easiest Change to Make Better Wells. My name's John McKenna, and we're going to be presenting some observations made from microseismic data as collected from a surface array. And when we collect microseismic events from a surface array, we can measure the focal mechanism. So we're detecting the P-wave radiation pattern at that surface array, and we can derive a focal mechanism that best fits that radiation pattern. And these are really important for modeling discrete fracture networks. We can invert for stress, and we have a better idea of which fracture sets are failing during the stimulation. And then through that stress inversion, we can tell you which fracture sets are more susceptible to failure and which ones require more pore pressure to reactivate. And in addition, we can give you more information such as which fractures are dilating more and which ones are not dilating as much, which comes to where the permeability is coming from. So there are two main types of focal mechanisms that I'm going to be talking about: dip slips and strike slips. The dip slip mechanisms are simply slipping in the direction of the dip, and the strike slips are slipping in the direction of the strike. And what I'm going to be showing is that oftentimes when you have offset wells that are being treated, you treat one well and you get dip slip fractures that occur in a normal stress regime, and then you go off and you treat an offset well, and when you have activity occurring back on the previously treated wells, those same fractures are changing from a dip slip rate to a strike slip. And the reason being is that there can be rotations in the stress state due to stress shadow effects, which causes the same fractures to be slipping, but in a different stress orientation, causing the rate to change from this dip slip to strike slip. And so what we can see is that is occurring, and that absolutely affects how your frac is going to be behaving, and that persists for some time and then goes away. And we can measure that time dependency, which can be extremely important in terms of understanding the frac itself. So what am I talking about? Well, we've got a lateral view and then a map view here. If you treat the upper well first, you get these cartoon-like red fractures, and then you treat the lower well, and you have these blue fractures. In the area that you have an overlap, that's where we're seeing compounding pore pressures. We're seeing the stresses are rotating in those areas, and the focal mechanisms are changing. Similarly, if you treat well 1 and well 2 in map view, we're seeing that there seems to be a rotation in between the two wells due to the stress shadow effect. The blue lines are showing the rotation in SH max. And when we create a heat map in terms of looking at the fracture volume in that overlapping area, that's where we're seeing the compounding pore pressures. So what does this mean to the operator? Well, what I'm doing is here I have a map view, these two top panels, and a depth view. We're looking at a horizontal distance from the stage center versus a longitudinal distance from the stage center. So it's as if we've taken all the data from every stage of the well and stacked it on top of one another. This is the targeted interval where we're expecting all your fractures to lie. And I've got the different perforations shown here in the middle. And then the contours are showing how we've modeled the proppant. What I'm showing in colors are you're going from this dip slip or your virgin stress state, your virgin reservoir stress, to strike slip, which is representative of this altered stress state. And I'm suggesting that where you see the cool colors, that's where your fluid is going. Where you see these hot areas, that's where you have these altered stress states that the rock is already stressed due to the previous treatment, and it's already pressured up, and it restricts your slurry propagation. So your fluid is contained in between. So I've got three different examples: an isolated well, a well that's treated without any other wells in the area, and we're looking at stage lag time. I call it DT. This is the time it takes to go from treat one stage to going over and treating the other stage. And so in the isolated case, you're breaking rock predominantly in this virgin stress state. Your fluid is contained right around the wellbore. Your proppant's contained around the wellbore. When you have this rapid stage lag, in this case we have a well located at about 900-foot offset on either side. They treated this side, and they treated this side, and then treated the center well within about less than a day, 0.2 days. We got a zipper frac arrangement going on. And when you treat the center stage, you can see that the virgin stress state events and your proppant is sandwiched in between the two wells. And we see SH max, the virgin stress state, oriented at about an 80-degree azimuth. And we have a left lateral rotation on the left side, and we have a right lateral rotation on the right side, similar to our theoretical example. Also, we have some stress on the toe side, which was the previously treated stage, pushing the treatment towards the heel. Now, what happens when you have a long stage lag? In this case, we treated the shallow well. This is a cross-sectional view, a shallow well, and then nearly 18 days later, we treated this lower, deeper well, and we see all the colors are cool, indicating that there is no longer a stress shadow located on the shallower well. So what happens, all your fluid and your proppant is propagating back to the previously treated well through the previously developed fractures from the shallow well. So this is the type of arrangement we want to avoid. We don't want to lose fluid away from the well that we're treating. So this is a time dependency that we can see. It's embedded in the focal mechanism. These focal mechanisms are measurements taken directly from how the rock is breaking, and we can see this happening. So what do the inversions look like? This is where we get kind of a little bit more into the details, but we have a virgin stress state where SH max is at 80 degrees. We have that left lateral rotation, and we have that right lateral rotation. And what I'm showing is that these slip linears, these are the fracture planes, and then the slip linears are plotted as poles or 90 degrees off from the strike. When they're radiating outward, they're dip slip, and when they're parallel to the great circle, they're strike slip. So I'm just demonstrating that we have in this normal dip slip normal stress regime area in the wolf camp, predominantly dip slip or radiating outward in the virgin stress state, where we have predominantly strike slip in both the left lateral and right lateral. And what's nice about how we do these inversions is when you plot all these slip linears, they all point to a single location, which is your minimum horizontal stress. And depending on the pattern that they make, we can solve for your stress anisotropy or phi, which is shown here 0.36. That means the distance between sigma 2 and sigma 3 is 36% of the total differential stress. So where are these rotations and virgin stress state events occurring? Well, the fluid or virgin stress state events shown here in blue. When we look at distance from the stage center, this is a lateral view, or horizontal distance from the wellbore. They're primarily right around the wellbore, and the left lateral rotation is primarily on the left side of the wellbore, and the right lateral rotation shown here in gray is primarily on the right side of the wellbore. This is due to the fact that when they were treating, the previously treated well was kind of lagging the second well in the treatment. It's important to note that these stress rotations will seem to wrap around any previously treated well, whether it's off to the right or off to the left or up above or below. We can see it in 3 dimensions. So this is just showing another example of what that looks like. When you treat your second well, we'll see that left lateral rotation off to the left, and the flip is happening off to the right. So why is this important? Well, we can track where these virgin stress state events are occurring. I argue that when you have these altered stress state events illuminating, that's an area where the rock is already pressured up. It restricts slurry propagation. So where you have virgin stress state events, this represents areas that rock is breaking under unpressured up air, situations. So that's more likely where your fluid is going, since your fluid is going to be moving away from these high pressured areas. So if we track just where the virgin stress state events are occurring, we can look at your perpendicular distance from your stage center as a function of the stage lag time, or your stage lag time as a function of your vertical distance. And they both show the same thing. When you treat wells in isolation, your frac is located right around the well that you're treating. But after some time, that stress shadow goes away, and we have virgin stress state events going off laterally to offset wells. Similarly, in this case, we see low stage lag time, events located right around the wellbore, and then propagating shallow towards the previously treated wells. In this case, the second well treated was typically the deeper well. So now I want to show another example where we have some tracer data. We're in the DJ Basin. In this area, SH max is at approximately 123 degrees, and this blue color indicates that the stress anisotropy is approximately 0.75. What we like to do is plot all of our focal mechanisms in terms of the active nodal plane. We've got this is a very complicated area. We plot all the active nodal plane. It's important to note that for any focal mechanism, there's actually two potential nodal planes that could be active, so we have to identify the active nodal plane. One way that we can verify this is we run a 3D lineament analysis. This is an unbiased look at the events. This is a time-space pattern recognition algorithm with outlier detection and noise removal. What we're doing is we're tracking these events as they occur in time and space, and we fit three-dimensional planes to those events and look at the striking dip that they're forming to make sure that they're illuminating the same orientation that we see in the auto MTI solution. As you can see, we have very similar results, so we can proceed with our analysis. Everything afterwards will make sense. So this is showing the fractures from the treatment, 7 wells in the DJ Basin. This is showing the treatment date as a function of the stage number. And so a lot of times when the operators go in, they say, well, we're going to treat this green well first, followed by the orange, then the blue well. We're going to treat the yellow well, followed by the cyan. We're going to treat the red, followed by the purple. But the problem is that the SH max is oriented at 125 degrees. You can see very clearly here. And so when you treat this well and you go over to the next one, you're pressured up well ahead of this one, so we have to actually consider this. So the easiest way to do this is we just rotate so that SH max is horizontal, and then we just plot the rotated northern coordinate of each stage versus time, and now we can very clearly see that the green well is leaving, followed by the blue, orange, etc. So this is a way that we can easily calculate our stage lag time, and which wells are feeding and which ones are trailing. And here's an example of our stress inversion, much more complicated inversion with very high horizontal stress anisotropy. So in this case, we're treating green, blue, orange, cyan, yellow, and then we come around and treat this red well and the purple well. And the important thing to note here is that by the time we treat the purple well, it's been 30 days since we treated the green well. And they injected tracer, well-specific tracer in each of these wells. We see each well here as solid lines. The dashed lines here were previously drilled and produced wells. So these are the parent wells. And so well 1 was initially treated first. These green, or the lines are showing approximate distribution of where the tracer was produced from. So for example, well 1, you look here, well 1, this is where they injected, and then this is where it was produced from. 85% of the tracer was produced back on itself, well 1. And then we see some of it was produced from well 2 and well 3 going over 2 to 3 over to here. And so what happened was they treated well 1 first. There was a pressure sink here due to the depleted well, so a lot of the frac energy went this way and set up the stage as now we have a pressure wave going off to the east. You treat well 2. It also shows treatment produced by itself but off to well 3, so it's following suit. Everything is now pushing off to the east. So each of these wells are being treated and their fluid is mostly propagating to the east. So you go 1, 2, 3, 4, 5, you come over here, 6, 7. By the time you get to well 7, it's been 30 days since you treated well 1. The stress shadow has gone away on well 1. Well 7, you only get 58% of your fluid contained around the well, and the rest of the fluid is going as much as, what is this, 4,000 or 5,000 feet away to all the way over to well 4. So this is an example of where that stress shadow has gone away on well 1, and well 7 is not well contained. So this goes back to one of our first slides. We can take advantage of these stress shadows if wells are treated in a timely fashion, but once that stress shadow has gone away, fluid could just propagate back to the previously stimulated well. So we can see these stress shadow effects occurring. Operators can take advantage of it. If they don't take advantage of it, we could lose a lot of fluid and we're not significantly stimulating the well that we're trying to stimulate. Thanks for your attention, and I'd be happy to answer some questions. The important thing here in the conclusions is this virgin and altered stress state can be identified by performing a stress inversion of these focal mechanisms. And the regions identified as experiencing this altered stress are regions experiencing high stress, likely higher remaining pore pressure, which would restrict slurry propagation from subsequent injections. Also, the fractures that are occurring in those areas have low dilation tendency. We're actually not creating a lot of fracture volume over there. After that pressure dissipates through the newly fractured network, new injected high pressure fluids can just go back to the previously treated well. So, hope you guys enjoyed that talk. And if you have any questions, I'm happy to answer. No, it's from using microseismic data. So when the events occur at depth, that radiation pattern goes up to the surface, and so if it's failing